So what we're going to talk about now is we're going to talk about energy. Now we've talked about work. Energy by definition is the ability to do work. Seems kind of a cop-out of an answer, but that's actually the definition of energy, is the ability to do work. And when we talk about work, remember that positive work is an attempt to speed an object up. Negative work is an attempt to slow an object down. So you can see where kind of energy and work, you can buy into this idea that energy is the ability to do work, which means that energy is the ability to either speed or speed up an object or slow an object down. Okay, so that is work, or not work, energy, the ability to do work. It doesn't necessarily mean that it is doing work. It just means it has the ability to do it. Now, going back, work, the definition of work is the integration of force dot dr, where r is just a generalized variable. Radius is just a generalized variable for position. Okay. It doesn't have to be on the x, y, z coordinate system. It can be in any coordinate system. That's why we use r. Okay, so simplified, after I take an integration for most forces, not for all, but for most forces, that turns out to be force times displacement. Okay, and remember, we're concentrating on forces and displacements that are in the same or in opposite directions. Nothing that's perpendicular to each other. Okay, so that is the definition of work. Now, to tie that into energy, we have to concentrate on particular forces. The first force, probably the most common force that we use in physics, is the force of gravity, the weight of an object. So when we talk about the work that can be done by gravity, we're talking about the energy associated with gravity. Well, the force of gravity is mg. Okay, so mg is equaling to the force of gravity. Okay, so when we look at the weight of an object, we take an object, and here's our object. We talk about the force from that object, mg. We know that that force is always going to be directed towards the center of the Earth. It's always going to be directed down. Okay, so that means that this delta r, this change in position, this displacement, can only happen in a direction that's either up or down. I don't want to use the word y, because you can see with objects on incline that I can switch those axes pretty easily. So it's not mg delta y, it's mg delta up, delta down, whatever that may be. So what we like to do is we say that's mg delta h. Okay? Or simplified, well, you'll see more often than not, is mgh. Okay, where h is height. So the change in an object's height, change in that object's height, is its energy. So if I have an object that moves all the way up here, if I take a ball and I move it all the way up to here, that means that it has energy. Force of gravity is this way. The height is this way, so that actually means that the gravity was working against the motion to bring it up. But if I bring that object down, force of gravity this way, the height is now gone down, the change in the height is now gone down, that means that gravity is promoting that motion. It's wanting to go in that way. Okay, it's doing positive work in that case. Cool? So that's the first bit of energy. That's gravitational energy. Okay, it's actually called gravitational potential energy, but we're going to stick with gravitational for now. We're going to talk about all these forces, then we're going to split them up into different categories from there. Okay, so there's one. The next force we're going to talk about is spring. Now, spring is one of those forces that are actually going to have us, we're going to have to do a little bit of changing up and actually do an integration on. So we say that the force of a spring is equal to kx. Okay? Cool? The force of a spring is equal to kx. There's a negative term there. I could put the negative in there, but then we would have to deal with this idea of what this dot product means. dx. If I take the integration of that, I'm going to get the answer of 1/2 kx squared. If you want to see that integration, either approach me or approach your math teacher. Either one of us should show you exactly where that comes from. Okay, so that is the energy of a spring, 1/2 kx squared. Okay, so we have another energy here. We have the energy inside of a spring, which is equal to 1/2 kx squared. Cool? So I'm going to write those down. I've got mgh, I have 1/2 kx squared, and then I'm going to have a whole slew of other forces. The one I'm going to add, well, static friction is going to do nothing for us, because static friction means that there's no motion. Well, there's actually no motion for that object, so we really don't concern ourselves with the work done by static friction, but we can consider kinetic friction. But it's pretty simple. The force of friction for kinetic is just the force of friction of kinetic. It turns out to be normal force times mu, if you want to put that in there. Times displacement. Okay, so it's not any it's actually a really simple equation. It really doesn't even deserve to have space on the board. Okay, and we can use the same process to throw in other forces. You can throw in a normal force. Now it seems kind of bizarre that a normal force will do work, but it does do work. If you're standing in an elevator and the elevator goes up, it accelerates you up, then the normal force on your feet is actually doing the work to lift you up. It's not the tension in the elevator that's doing work on you. I hope not, because that means that that cable, that string, has to be attached to you. It's attached to the elevator. The elevator is being lifted up, and then the floor of the elevator is lifting you up. Okay, so you can say normal is in there, delta y. You can throw in a whole bunch of slew of other equations, okay, but these are really not that important. They're there. You can use them as an equation. You'll probably use this one. You probably will never use this one. It's just not terribly useful. You have these equations, and there is one more that's really, really important, and it goes back to F. Now we know from Newton's second law, the true form of Newton's second law says that net forces change momentum per unit of time. But if the mass of that object doesn't change, we get another equation. We get net forces is equal to mass times acceleration. And I'm going to use that for my definition. So right here I'm going to substitute in ma. Okay, dot dr. Well, we know that ma, or a at least, is equal to the change in velocity over the change in time. Okay? Do a little bit of moving around of variables and I end up getting this. I end up getting okay? Well, dr over dt is v. Okay? The change in position with respect to time is v. So what I end up with is I end up with this equation. I end up with mv. Oh, that's kind of strange, because mv is equal to momentum dv. Okay? So the integration of momentum with respect to velocity. And that gives me, bringing it back, 1/2 mv squared. Okay? Yet another equation. This one's different than all of the other ones for one simple reason. ma. That's not a force. That's the result of all forces. Okay? So it's a little bit of a different animal. Okay? I'm going to go ahead and write it up here, but I'm going to write it separating it from everything else. Okay? Cool? So, what we end up with the first one. Gravitational potential energy. We end up with the second one. This is actually spring potential energy. Okay? And then we have a whole series over here that are just nothing more than force times displacement. Okay? Which we call work. Okay? And then we end up with this one right here. Okay? So what we actually get out of this is we get two new vocabulary words. The first one being potential energy. Potential energy is energy that's based on position. Okay, the first two, if you look at them, mgh and 1/2 kx squared, they're positional based energy. They're energy that's based on the position of an object. If you take the first one, its energy is based on where that object is located. If it's up high, it has more energy. If it's down low, it has less energy. Okay, so positional based energy. The next one, the compression of a spring, or stretch for the spring, for that matter, that kx squared is just stretch or compression. So if I compress a spring or if I stretch a spring, I have energy, but it's where that object is being compressed to or stretched to that gives it the energy. Okay? So these two are called potential energies, and potential energy is nothing more than positional based energy. It's energy that's based on the position of an object. Okay? Cool? These we typically just call work. These forces times distance we just typically call work. Okay? You know, normal times y. Force of friction times displacement. Those are all just work. We don't really give them the category of potential energy. We don't really give them the category of anything other than just work. Okay? Because those are just kind of random forces that are out there floating around. The last one, at 1/2 mv squared, motion. It has nothing to do with position. 1/2 mv squared has nothing to do with position, has everything to do with motion. And because it's a v squared, it gets rid of direction. It doesn't, velocity this way, if it's in the negative y direction, which would be whatever, negative y direction means that velocity value is negative, so it could be -3 meters per second. But if I square -3, I get 9. Okay, it just tells me how fast it's moving. It doesn't tell me that it's -9, where it just tells me that it's 9. Okay, so this v squared is referring to the speed of the object and not necessarily the velocity of the object. This one is called kinetic energy, motional based energy. Okay, so you've got your potentials, you've got your kinetics. And the other interesting thing that we've been floating around, and we've got these potentials, which are positional based energies, these kinetics, which are motion based energy. There's actually a rotational equivalent to this one, where it's rotational motional energy. The interesting thing about this is that when we refer to the work on an object, typically what we're doing is we're transferring from one form of energy to another. So if you can think about shifting from gravitational energy to spring energy, there's work that's being done shifting that gravitational energy to spring energy. It's taking a mass and putting it on a spring. The mass compresses the spring, so that gravitational energy, that mgh, shifts into 1/2 kx squared. There's work that's being done to do that. Or to take gravitational energy and convert it into kinetic energy. There's work that's being done to do that. Okay? So these are our primary types of energy. There are other types. Nuclear energy, thermal energy that we will talk about. But we just want to start with these to begin with. Okay, so gravitational or potential energies, work forces. I mean, they're all work, but we tend to think of these as just being work. We don't give them their own category. And then kinetic energy. Okay, so that's kind of what energy is.